Hello, everyone. Thank you for joining the fifth installment of our webinar series. We have a great presentation we are excited to share with you today. My name is Misha Lalou, and I am the marketing specialist for DynaEnergetics, and I'll be the host for today's webinar. Our panelist today is Dr. Jörn Löhken. Jörn is the Technology Research Manager here at DynaEnergetics. He has been with the company for 9 years. During his time here, Jörn has developed numerous products, created various US patents, and has written and presented several SPE papers. So Jörn, thank you for being on the call with us today.
Good morning.
Today's webinar format will be slightly different from what we have done in the past. Jörn will be presenting on the experimental investigation on parameters affecting the coefficient of discharge. Before I hand it over to Jörn, I would like to point out that throughout the call, if you have any questions, please type them in the Q&A function, which is located at the bottom of your screen. We will be monitoring all the questions that come in, and we will be answering them at the end of the call. So we have a lot of great topics we'll be covering for you today. So Jörn, thank you again for joining us, and I'm going to go ahead and hand it over to you.
Yeah, good morning, everybody. In the webinar today, I'd like to present the results we get during our experiments on the coefficient of discharge and on the parameters which affect this coefficient of discharge. So in the following slides, I'd like to first say something about the geometry influence on the coefficient of discharge of perforations. This coefficient of discharge is actually a measure for the effectiveness of a perforation. So I'll start with an introduction and motivation, briefly explain the test setup. We will then talk about the geometrical parameters affecting the coefficient of discharge and see what we get for real perforations. And I'll also say something about the importance of hole size measurements. In the second part, I will more concentrate on the effect of backpressure and erosion and summarize in the end. So until now, for conventional reservoirs, people were mostly looking at penetration depth as this is the most important feature of a charge. So we have 3 API tests for its evaluation, but for unconventional reservoirs, actually the hole size is the most important parameter. We see this with the importance of equal entrance hole charges on the market, but there are not so many API tests at the moment. We have a section 7, which is coming, but we thought there is a need to evaluate the flow performance of perforations. Why this is important, I'd like to explain on the next slides. If we look at a well for fracturing with a horizontal casing, we have in the casing a bottom hole treating pressure, which is actually given by the hydrostatic pressure and your surface treating pressure on the one side of the casing, and on the other side you have your fractures with a fluid pressure inside of the fracture and a fracture closure pressure. And driven by this pressure difference between your bottom hole treating pressure and the pressure in the fracture, you have a certain flow which goes into your fracture. But not every fracture is the same due to variations in the geology. For some, you might have a fracture closure pressure of 3000 psi, and for other ones, it might be as high as 3500 psi. So for one and the same bottom hole treating pressure, the pressure drop over the perforation might be different. So it could be 1000 psi for the one perforation and 500 psi for the other one. What that means is 100% difference in pressure between the 2 perforations and the 2 fractures. And actually it also means that you have 42% difference in flow into your fractures. So the volume of fluid which goes in one fracture is 40% higher than in the other fracture. To mitigate that, when it's usually the people increase the pressure in the casing by limiting the entry. So if you increase the bottom hole treating pressure from 4000 to 5000 psi, you can see that these pressure drops now become larger, and we have 2000 psi for the one fracture and 1500 for the other one. And so the difference in pressure is only 33% in pressure and 15% in flow. and your two fractures will grow more equally. The question is now how you can achieve this increase in pressure. And like I said, you limit the entry. And to understand that, I've given here the equation which is used to calculate the pressure drop. The pressure drop over the perforation is mainly depending on the flow rate. It goes with the square of the flow rate. So the higher the flow rate, the higher your pressure drop. Also, the number of perforations are quite important. And one of the most important parameters, because it goes with the fourth power, is the diameter of the perforation, as well as the coefficient of discharge. And if you rearrange this equation that you use instead of the diameter, the surface area, you can see that the surface area of the perforation as well as the coefficient of discharge are of a similar importance for this pressure drop. So what can you do to increase this pressure drop? You can either reduce the number of perforations or you can reduce your entrance hole diameter. The importance of the entrance hole diameter can nicely be illustrated on the example of equal entrance hole charges, as they are quite popular at the moment. And I have two examples here to illustrate that. On the left side is a generic example for a normal charge with an entrance hole diameter of 0.35 inches and an entrance hole variation of approximately 10%. What that means for the entrance holes is that you might have a quite small entrance hole on the high side because your gun is decentralized, and so the distance to the upper side is larger. And that means you have maybe 2 barrels per minute going through this upper perforation, while on the low side you have a 0.4 inch hole, and 3.6 barrels per minute in this example will flow through the perforation. So you have a variation of 80% between the different perforations and a variation of 19% in flow. That can be mitigated by using modern equal entrance hole charges like halo frag, frag tune charges, which have a reduced entrance hole variation. In this example, we have taken an entrance hole variation of only 3.5%, and that means that the difference between the high side and the low side is not that large anymore. And the flow is 2.4 barrels per minute in this example, and 3 barrels for the lower perforation, and the maximum deviation is now only 25%, and with equal entrance hole charges, you can reduce this difference in flow amount going into your fracture through the different perforations. But what about the coefficient of discharge? As I've explained, the coefficient of discharge is actually of a similar importance as the surface area of a perforation. This coefficient of discharge is a measure for the effectiveness of your flow. So actually, it's the ratio of your actual flow through the maximum theoretical flow. This can be illustrated on this small picture here. We have a container with a small orifice. And as you can see, the flow through this orifice is not occupying the complete area of the orifice. It's actually contracting, and this is called a Werner contractor. So the flow doesn't take the complete surface area. The ratio of the used surface area to the possible surface area is also proportional to the coefficient of discharge and the measure for it. This coefficient of discharge is depending on the geometry of your hole. So as soon as you increase the thickness, for example, this coefficient of discharge will increase from 0.7 in this example to 0.8. Also, if you taper your entrance, it will go up to 0.9. And if you have a nice rounded entrance, it can be as high as 0.95. You can see by that there's a huge variety of values which might be right for a perforation hole. What that means for your flow rate or for your pressure is, I want to illustrate that on two small examples. So for a given pressure, a difference of 0.95 to 0.7 as a CD factor means you have 30% difference in flow. Or if you have an identical flow rate, you will have 46% less pressure if you have a CD value of 0.95 compared to 0.7. So this is very sensitive, the pressure, this coefficient, and therefore we thought it's worth looking in more detail into it and to find out what is the right value for a perforation. On this slide, you can see a picture of a perforation. we photographed the inlet side, and you can see the small burr. On the outlet side, on the right side of the slide, you can see an even larger burr. And what we did in addition, we did a 3D scan of this hole. And in the middle, you can see a cut through this 3D scan. So this here is the tunnel of the casing. And on the inlet side, you can see the perforation is slightly rounded. The shape is not cylindrical, it's conical. And in relation to the diameter, it's also relatively thick. So actually, a perforation has something from all these examples. And so, yeah, it will be interesting what is the right choice for the coefficient of discharge. In the test setup we used a high pressure pump to have realistic inlet pressures. This pressure pump was connected to a test cell, which is shown here. It consists out of two 7-inch pipes with a casing plate in between them. On the outlet, we had a choke, which later on gave us the opportunity to have a back pressure on the outlet side. And then the fluid was going into a tank. This test cell, which we've used, is shown here. And you can see here the casing plate. To calibrate the setup and to look at general dependencies, we first worked with machined plates of different hole sizes, of different casing thicknesses. We used plates with a conical hole and also with tapered inlets as well as slots. In the second step, we used perforated plates, which we took from API section B, 19B section 4 tests. That means these shots were made under the most realistic conditions with a wellbore pressure, with an overburden pressure on the target and the cement sheet behind the casing. We used all of the charges which are used for fracking operations like Trinity, Fractune, DPEX, HaloFrac charges with gram weights between 8 and 39 gram. The measurements we took are shown on these slides. So in the first step, we left the outlet pressure constant and increased step by step the inlet pressure. And for each pressure, we recorded the flow rate. And so for each couple of these values, we got one data point. As you can see, we did that for different pressures. And so we have different data points for each hole size. The equation shows you we have a quadratic behavior between the flow rate and the inlet pressure. And this is exactly what the equation has told us. So it's a good confirmation of the test setup already. These three examples show data measured for 3 hole sizes from 0.3 to 0.4. And you can see with a larger hole, you get more flow at the same pressure. For each of these data points, we now calculated the coefficient of discharge based on the equation which I've shown previously. And this gives you this curve. So for the different inlet pressures, you can have a coefficient of discharge. And first of all, we can see that it's more or less flat over a broad range of inlet pressure as long as the back pressure is not applied. So we have an ambient pressure on the outlet side. For this example, where we have 3 different hole sizes, it's visible that there's not really a trend. So from that, we would say that the hole size has not a huge effect on the CD value. It's a bit different when we look at the thickness of the casing. In this example, we made experiments with 3 different thicknesses from 0.29 inches over 0.47 inches up to 0.94 inches. And for the thickest one, we really see a significant deviation, also the trend in the data. And so we would say that thickness is important for the coefficient of discharge, and this is also in accordance with the theory presented on the introduction slide. More interesting is even the comparison of the different shapes of the perforation. So we have a base case with a cylindrical hole, and we compare this with a conical hole where we have a larger opening to the inflow, with a conical hole where the opening, where we have a sharp edge on the inflow part and it's opening towards the outflow. And we have one situation where we just have a small chamfer of 0.02 inches on the inlet part. The sharp edge actually gives slightly smaller values. We called it conical trumpet shape. Than the cylindrical one, and this might be due to this sharp edge, which maybe cause turbulences on the inlet. But already, if you have only a small chamfer, you increase the flow rate, and therefore your coefficient of discharge is increased really by this small change in geometry. And as expected, the conical funnel shape has the best flow properties, so your coefficient of discharge is the highest for this situation. With this, we went into the experiments of the perforated plates. And for all 12 of them, I will show now the results on one slide. Again, we have the coefficient of discharge as a function of the inlet pressure. And what becomes visible is that the variation is quite large. And also the values are slightly higher than the values we've seen for the machine plates. To investigate in more detail why we have these higher values, we looked at the special shape of the perforation, and also we were interested if the cement on the backside of the perforation has an influence. The results of that are shown on this slide. So first of all, we have the casing plate with a cement layer behind it. And for the flow experiment, we got a value of 0.85. We afterwards removed the cement and repeated the test, but we haven't seen actually a difference in flow, and therefore also the coefficient of discharge is the very same. The situation changes when we milled away the inlet burr of the perforation. You can see it on these two pictures. So we took it completely away, and again, you get a kind of a sharp-edged inlet, and hence the coefficient of discharge dropped by 0.1. So it seems that the inlet really acts like a funnel or like a chamfer and increases the coefficient of discharge, and as soon as you take it away, it drops again. In the last step, we also removed the outlet burr, but this has not affected the flow anymore. So this outlet burr is of sort of a significant importance for the flow measurement. Another thing which is important for the deduction of the coefficient of discharge is the entrance hole measurement, because we always measure the flow, and to deduce a coefficient of discharge, we have to assume a certain hole size. But yeah, hole size measurements can be done in different ways, and this can lead also to slight deviations in the entrance hole, which you get from these measurements. The most common way to measure entrance hole sizes are caliper measurements, as they are used also for API 19P section 1 tests, where you measure the maximum and the minimum hole size. And from that, you deduce an average value. And this can also be illustrated here on this photo with the red line and the blue line, the minimum and maximum value. And you can see an ellipse, which is built by these two axes. And actually, it doesn't cover all parts of the hole. So there are some bright spots which are not covered. And so this measurement of 0.29 is maybe a bit too small. Another possibility to measure the hole size is by optical measurements. So you photograph your hole, and then with the software, you can measure the hole size. You can use either an automatic algorithm, and it determines just the bright area of your hole. And from that, it really covers nicely the complete bright area. And you get a value which is slightly higher than the one with the calipers of 0.3 inches. But looking in more detail at the perforation, it's a more complex geometry. So first of all, the direction of the perforation might be slightly tilted against the axis of your picture. So therefore, you always have to consider the optical axis. Second, the smallest diameter of a perforation hole is not necessarily at the surface of the casing, but it might be in the center. So your calibration must be made for the right distance. And due to that, we made a manual interpretation of all pictures where we determined, and we are really step by step for each hole, the surface area manually, and then we get a larger value of 0.32 inches. What that means for the coefficient of discharge is shown on the next two slides. First of all, this is the result for the automated image processing. And you can see still the coefficient of discharges are shown with the blue bars, and the entrance holes are given by the black line. You can see that we still have very high values, and there's it's a huge variance between the different holes. For this charge 8, for example, we have the entrance hole of 0.29, and the corresponding coefficient of discharge is as high as nearly 0.9. If we now look at the results of the manual image processing, then we see a much smoother coefficient of discharge distribution, and the values also dropped. So again, for this charge A, the entrance hole is now larger, but at the same time, the coefficient of discharge went down to 0.7. And that clearly shows that these two values always have to be measured in parallel to really have the optimal value for your pressure drop calculations. These values of 0.7 to 0.8 are values which are commonly used in the industry for the coefficient of discharge. So it's in line with values which are used by operators. As a first summary, the entrance hole has a huge effect on the fluid flow, which explains the importance of limited entry and equal entrance hole charges. We've seen that the coefficient of discharge is as important as the area of the perforation hole for the calculation of the pressure drop, and it's influenced by the hole geometry and the casing thickness. For perforation, we've seen that bursts on the inlet side of the perforation really significantly affect the magnitude of the CD value, and that the values measured for real perforations really strongly depend on the method which is used for hole size measurement and its accuracy. In the second part of the presentation, I'd like to concentrate now or put the focus on two other things which influence this coefficient of discharge, which is the back pressure on the outflow part of the perforation and the role of erosion. The back pressure is actually representing the fracture pressure you have. So a setup where you have an inlet pressure, which is representing your casing, bottom hole treating pressure, and then back pressure, which is representing your fracture pressure, is the most realistic setup you can have. And to measure that, we used the very same test setup and increased the inlet pressure as high as we could. And then step by step, we closed this choke. And by closing the choke, we established a back pressure. And so the pressure difference became smaller and smaller with increasing back pressure because we kept the inlet pressure constant. And what we measured is shown on the next slide. First, the black curve shows what we've seen previously in the experiments. We kept the outlet pressure at ambient pressure conditions, increased the inlet pressure, and on this graph, the pressure difference is now plotted versus the flow rate. And with increasing inlet pressure, your pressure difference goes up, your flow rate increases, and that's what you expect. When we reached 1,400 PSI inlet pressure, we kept the inlet pressure constant and now closed the choke, and therefore the back pressure was increasing, and with increasing back pressure, your pressure difference was getting smaller again. Surprisingly, although the pressure difference was now going down, the flow rate was still at a very high level, and only with a pressure difference of 600 PSI, and this flow was also decreasing. And this was really surprising for us because this is not in line with the equation for the pressure drop. What that means, we wanted to illustrate this on this slide in another way to display the data. Again, we plotted the flow rate, this time for a constant pressure difference for different back pressures. So we kept always the difference between the inlet and the outlet pressure constant and simultaneously increased both pressures so that DP was always the same, but the back pressure was getting higher. And although the DP was the same, with increasing back pressure, the flow rate was increasing. And that means for this equation, you can only explain it if your coefficient of discharge is also increasing. So actually, in this case, with increasing back pressure, it was going up from 0.7 to nearly 1. We did these experiments not with only one inlet pressure, we did it also with different inlet pressures from 1885 down to 870 PSI inlet pressure. And for all these inlet pressures, this phenomenon of increasing CD value was observed, but at different back pressures actually. So we were looking for a correlation between inlet pressures and back pressure. And when we discussed that, we thought of an observation we made during the testing. And at the very beginning, where we had ambient back pressure, the setup was very loud. And as soon as we closed the choke and established the back pressure, this loud noise was vanishing. And yeah, during the discussion, it came up that this can be due to cavitation. Cavitation means that your fluid is vaporizing locally. You have gas bubbles which build up and then later on collapse again. And this makes this high noise. This can be explained by Bernoulli's equation. So for a given flow, your local pressure will always be a sum of the static pressure and your dynamic pressure. So the dynamic pressure is proportional to your flow velocity, and your static pressure is just adding up to this equation. And of course, you have a hydrostatic pressure as well. But as this is constant throughout the complete profile, whenever you decrease the diameter, your speed will go up, and therefore your static pressure has to go down. And when your speed is really high, so in an orifice or in a perforation, then the static pressure can go as slow as your vapor pressure. And actually it can go even below it, and then you have this effect of cavitation. And this can be expressed in the number called cavitation number, which actually is the relation of this static pressure to the dynamic pressure. So it's depending on your flow velocity. And whenever this is smaller than 1, it's likely to have cavitation. Of course, also the vapor pressure of the fluid has to be considered in this equation. We rearranged now the data from this slide where we plotted the coefficient of discharge as a function of the cavitation number. And this can be seen in this slide. So for all of these data points, we plotted them, and for very small back pressures, the cavitation numbers are small, and we see a nice linear increase of the coefficient of discharge with the cavitation number. And as soon as the cavitation number of 1 to 1.5 is reached, it goes to a constant level of approximately 0.95. And that was, surprising for us, but also it's a nice correlation. And actually, we've seen this behavior for all of the machined plates. It was seen for all of them, even for these conical ones, which are representing these two curves. It's just not of the same magnitude, but also for these two curves, it rose till approximately 1 and then stayed at a constant level. I want to show also the example for 2 perforations. We made the same measurements for all perforations, but I just picked 2 of these perforations. And also for these 2, you can see that the coefficient of discharge seems to be a function of the cavitation number, and with very high back pressures, so with very high fracture closure pressures, your coefficient of discharge increases and stays constant at values above 0.9. And as I mentioned previously, normal values, which are given in the literature, are in the range of 0.7. So the values we've seen here, we have also 0.7, but only at ambient pressure. And when we apply back pressure, these values go up to 0.9 and 0.95. In the second part of this research, we looked at the effect of erosion. For that experiment, we modified this setup slightly. We made a closed loop with a hopper for sand injection, and then circulated the same fluid for 30 minutes through the setup. We were interested in the very first moments of erosion, where the shape of the perforation is changed due to erosion. In the second step, the hole normally grows, which is more related to the steel properties. But yeah, we were more concentrating on the characteristics of a perforation hole. So we've chosen quite a small pressure differential of only 200 psi. The flow rates were, depending on the diameter, of course, between 0.5 barrels per minute up to 1.5 barrels per minute. For each test, we used new sand with a grain size of 7 to 140, with a low sand concentration of 1 to 2 pounds per gallon. We used a viscosifier, and we did this test for 30 minutes, which means we've flown approximately 2,000 pounds of sand through the perforation. I want to first start with the example of two machined plates. These were holes which were drilled with a 0.35 inch diameter and 0.4 inch diameter. The dashed lines show the measurements before the erosion experiment, and the solid lines show the results after the erosion experiment. Again, the coefficient of discharge is plotted as a function of cavitation number, so which means also a function of the back pressure. For this charge G2 with a smaller diameter, you can already visually see that the rounding is not that much compared to the other one. From these two experiments, we wouldn't say it's related to the hole size. We just see a difference for these two experiments, but to really see a dependency on the hole size, we would have to do more experiments. But what is visible for G2, you see an increase in the coefficient of discharge just due to the rounding of the inlet. And for just this second plate, G3, this effect is even more pronounced. And actually, it seems that for low cavitation number, the increase is smaller than for high cavitation number. So this effect of erosion on the coefficient of discharge might be related to the cavitation number. I also want to share two examples of perforation holes. These are the examples A and B, and you can see them again before the erosion and after the erosion. Again, we see this rounding of the perforation. And for perforation number A, you can see that actually at low cavitation numbers, the effect of the erosion is not very large. Again, the dashed line shows the result before erosion and the solid line after the erosion. But then with higher cavitation number, we see a huge jump in the coefficient of discharge. And for charge B, actually, it's very, very similar, just the effect is much bigger for this one. To understand in detail why we see these differences in these two perforations, we looked in detail at the geometries of these two perforations. Again, we did 3D scans of the shape and the tunnel of the perforations. And these scans are shown here in these two pictures. The blue surface shows the surface of the perforation after the erosion experiment, and the transparent surface shows the surface of the perforation before the erosion experiment. So whenever there is the same, nothing was eroded, and when there is a difference visible, this is the material which was taken away by the sand grains. For this charge A, we can see that the diameter of the perforation really has not changed. So this increase in coefficient of discharge is only caused by this change of the inlet geometry. For the second charge, also the diameter has not significantly changed, and mainly the inlet geometry was changed, but also some small edges on the perforation, they were taken away. You can see here the small edge in this picture, and here it's already rounded. And you can see it also here in this top view, that this transparent part was completely eroded away, and we assume that this has caused this larger increase in the coefficient of discharge, although the surface area has not significantly changed. So to summarize the second part, we've seen that at high back pressures, the coefficient of discharge increases significantly. We've seen a correlation with the cavitation number. The cavitation can easily be calculated based on the fracture closure pressure, on the flow rate, the number of perforations, and the hole diameter, which are values you normally have. For usual fracking conditions, the cavitation number is much larger than 1 due to the fluid pressure in your frac. So based on our research, we would think that CD values of 0.9 to 1 can be assumed. What that means, again, just an example, if you use a standard value of 0.7 compared to 0.95, it means really you have 46% less pressure for the same flow rate. So it really makes a difference which coefficient you use for your calculations. Just for completeness, I'd like to mention that we've seen no difference in the measurements between water and gelled fluids, also for back pressures. For higher concentration of gelled fluids or cross-linked gels, that might differ, but it was not part of this study and would require more research. In the erosion tests, we've seen that erosion leads to an increase of CD, which is not surprising. But obviously, this effect of erosion also seems to depend on the cavitation number, and so that indicates that the effect of erosion depends on the pressure condition. And so some erosion models, they should be deduced at the right pressure conditions or must be updated accordingly. We identified three mechanisms which cause an increase in CD. Two of them are really well known, like the rounding of the shape of the inlet as well as the increase in diameter. But in this example, we've also seen that the removal of small corners, edges, or inhomogeneities on the surface of the can lead quickly to an increase of CD as soon as they are eroded. Yeah, with this, I'd like to thank you for your attention. And I give back to Misha.
Thank you so much for all the information you provided with us today. Definitely a very interesting and topical subject. So again, thank you. We have had some questions come in through the Q&A. So now I just want to transition to answering some of those. So Jörn, our first question for you is, what do the results mean for some future strategies?
Yeah, so based on the methods we did, we would think that the coefficient of discharge, or if you make a calculation of your pressure drop, you should use higher values than 0.7. And when you use values like 0.95, your pressure drops will be smaller, as explained previously. And therefore, I would look for strategies with less perforations, that you increase your pressure even more to get this limited entry effect. So either you take less perforations per cluster, or smaller entrance holes. But I would go for less perforations.
And the next question we have here is, what will the next erosion test setups and experiments look like?
Yeah, for the next test series, we want to concentrate more on the effect of the orientation of a hole in a casing. So we will change the setup slightly and look at casings which were perforated instead of casing plates. We've seen previously that for flow tests, it doesn't make a difference, but we want to make sure that for erosion tests, we are really using the most realistic setup. So we'll look at erosion at back pressures for different facings, hole sizes, and we want to make sure that we really always have the same sand concentration so that we can also deduce erosion rates.
So I think we're about out of time for today's webinar. Thank you to Jörn again for your time today and for a great presentation. And thank you to everyone for attending, for all of the questions. If you have any other questions, please submit them to either the email addresses that you'll see here on your screen in a second. You will also see a QR code on the right side of your screen here in a minute. And if you open up the camera on your phone and scan this code, it will take you to a survey where you can provide us with feedback on today's webinar. Would really appreciate any comments, any questions you have, any other feedback you can provide. If there's any topics that you're interested in hearing from us next on, please let us know. And again, thank you for attending, and we look forward to having you in our next webinar. Details for our October webinar will be coming out soon. Thank you, everyone.